Hello. This lecture will cover pages 251 through 255 of my lecture notes. Please print those pages out and have them in front of you as I present this lecture on digital arithmetic 6A, in specific binary addition and representing signed binary numbers. If you take a look on page 251, we're going to first investigate unsigned binary addition. We're going to have two nibbles here, A3 through A0 and B3 through B0. And we're only interested in adding up these two digits right here. If you take a look, we have column A0 and B0. Here's the A0 and here's the B0. Their possibilities are 0, 0, 0, 1, 1, 0, 1, 1. Just this first column here, just this least significant bit is all we're interested in. If they're both zeros, you get a sum of 0 and you get a carry of 0. That's pretty easy to see. If one of them's a 0 and the other one's a 1, it doesn't make any difference which order. You end up with a 1 as a total. A sum of 1 with no carry in either case. But what if they're both 1s? What if there's a 1 here and a 1 here? Well, a binary 1 and a binary 1 add up to a binary 2. So you'd get a sum of 0 and a carry of 1. But how would that look like over here? Can you picture a 1 being here and a 1 being here? When you add up the 1 and the 1, you get a sum of 0. And then you carry a 1 around to here and brings a 1 down to this point, assuming these were both 0. You get a 1, 0, which would be a 2. So briefly, a 0 and a 0 will give you a sum of 0 with a carry of 0. Either a 0 or 1, or a 1 and a 0 is going to give you a sum of 1 with a carry of 0. But what if you have a 1 and a 1? A 1 and a 1 will give you a sum of 0 and a carry of 1. Let's take a look at 4-bit unsigned addition here. I want you just to go ahead and take a look. We have a binary 3 unsigned. We have a binary 10 unsigned. We add them up. We get a 1 and a 0. You get a 1. 1 and a 1 is a 0 with a carry of 1. Gives you a 1 down here with no carry and a 1 down here. That adds up to a 1, 1, 0, 1, which is a 13. 3 and 10 are 13. What about this one down here? This is a 44, unsigned binary number. A weight of 16, a weight of 32 and 12. 32 and 12 is 44. Here's a binary, unweighted 26. 16 and 10. 16 and 10 is a 26. When you add those up, you get a 0, a 1, a 1, a 0 with a carry of 1, which gives you a 0 here with a carry of 1, which gives you a 0 here with a carry of 1, which gives you a 1 and a 0. That's a 70. If you take a look, it's a weight of 64 plus 6. It's a 70. 4-bit unsigned addition. Just gave you two examples there. What about representing signed binary numbers? We're going to discuss three notations. We're going to discuss sign magnitude. We're going to discuss 1's complement notation, and we're going to discuss 2's complement notation. And we're going to mention how they're used and if they're used anymore. Out of these three, you're responsible for all three of them. But the most important is this 2's complement notation. In this lecture, we're going to investigate sign magnitude and 1's complement. In the next lecture, the entire lecture will be devoted to 2's complement. Before we start talking about these three different types of notations, I want to talk about sign in general. A -1 or a -20, you can't show it. I mean, on paper, you can show that as a -1 and a -20, a full byte. But how would you represent that in a computer? Well, what computer scientists decided to do as a convention is take the leftmost bit, and if it's a 0, it represents a positive number. And if it's a 1, it represents a negative number. So let's take this full byte here. That's 8 individual bits. If this most significant bit. It's no longer going to carry any significance with regard to weight. It's going to be a sign bit. And if this bit is a 0, that's a positive number. And if this bit is a 1, that represents a negative number. So I'm going to introduce you to the signed binary number notations now. Keeping this in mind as we go through all three notations. We're going to start out with sign magnitude. Sign magnitude is probably the easiest to understand. Basically what you do is you take a sign bit and the rest is entirely magnitude. No, that's not going to be the way we interpret 1's complement and 2's complement. You'll see that in a minute, but just stay with me here on sign magnitude. Sign magnitude, this is going to be a sign bit, which it is for all of them, but the remaining bits will all be magnitude. So let's take a plus 7. We'll keep it simple for now. A plus 7 is a plus, and then you represent a 7 with the remaining 7 bits. There's a 7. A plus 7 using sign magnitude is this way. A minus 7 would be a minus 7. Well, let's add these up and see if you get 0. Well, there's a plus 7, there's a minus 7, and when you add these up, you get a 0, a 1, a 1, a 1, a 0, 0, 0, 1. Now you have to interpret that. Keep it in mind, we're working with sign magnitude numbers. If you convert to sign magnitude and you convert to sign magnitude, you have to interpret in terms of sign magnitude. Well, this number isn't 0. When you take a plus 7 and a minus 7, you should get 0. Well, there's your plus 7, there's your minus 7. You add them up, you get a minus 14. This is a minus 14. You know it's a minus number because there's a 1 there. It doesn't work. Sign magnitude doesn't work in arithmetic. Let's look at another possibility. What about a plus 12 and a minus 12? Here's your plus 12, sign, the rest is magnitude. Here's your minus 12, sign, and the rest is magnitude. When you add those up, you should get a 0. Well, we're just going to add these up using our binary arithmetic. And when you're done, you take a look at your answer, and you have to interpret that answer in sign magnitude. That's a negative 16 and 8. Negative 24. It doesn't work. What about a plus 16 and a minus 4? You should add them up and get a plus 12. Here's your plus 16 plus 16. Here's your minus, and the rest you have to represent a 4. There's a 4. There's a minus 4. Add them up, you get a minus 20. That's a minus 16 and 4. That's a minus 20. It does not work. Therefore, based on the above example, sign magnitude notation is not good for arithmetic operations. But you know what? It works great if you just want to store physical parameters such as temperature or pressure and express them as a signed binary number. Like a plus so many degrees centigrade, or a minus so many degrees centigrade, or a plus temperature, or a minus temperature, which would represent a vacuum. It's very useful to store numbers as signed magnitude numbers using this notation, but it's can't be used in mathematics. That is sign magnitude. The next notation we have to talk about is 1's complement. Do not get 1's complement and sign magnitude mixed up. They're two different notations. 1's complement notation. If you complement or invert each bit in a word, the new word is called the 1's complement of the original word. Doing this creates a very promising possibility for adding and subtracting signed binary numbers. Let's do some 1's complement math examples now. Keep it in mind, we're using 1's complement notation. This is the way you would show a plus 12 in 1's complement. Notice a plus 12 in 1's complement notation is the same thing as a plus 12 in signed magnitude. Matter of fact, you're going to find out, and this is very important, so listen to what I'm saying right now. all the positive numbers are represented exactly the same way, independent of whether you're using this notation or this notation or this notation. Positive number, you can't tell whether you're using this this or this or this with positive notation. You'd have to be told, because when you see a bit out here in the sign bit, at that point, that's where the notations differ from one another. But positive numbers, you can't tell the difference. So here's your plus 12 using 1's complement. What's a minus 12? Well, in 1's complement, a minus 12 is just the invert or the complement, the 1's complement of the plus 12. So you just invert each bit. Pretty simple. You just invert each bit, and that is a minus 12. Now, it's not a sign magnitude. You would have to be told that's a 1's complement number. What does it represent? Well, what you would do is you'd know it's a negative number, and you'd have to invert every bit to go back to this and say, oh, it's a minus 12. So I'm showing you a plus 12, showing you a minus 12. And you're going to go ahead and add these up. When you add these up, you get a 1 and a 0, you get a 1, a 0 and a 1, a 1, a 0 and a 1, a 1. Well, since it's a complement, you're going to get all 1s, and you're not going to get a carry in this last bit. Go through it, each one of them. You'll see just 0 and a 1, a 0 and a 1, a 1 and a 0. It's an inversion of one another, so you're going to get all 1s here. No, you have to interpret that now. You're going to have to interpret that as, what is that? That's a negative number, but what does it represent? It's an invert everything and you get a 0. It's a negative 0. Negative 0, a positive 0 is the same thing. You get a 0. It seems to work. But I can add a 1 down here if I want to. And if I add a 1 and I add them all up, I get to 0. I can use this 1 as a correction if you want to. You don't have to here. You just have to interpret this. Let's do another one. Here's a plus 12 and a minus 6. Add them up, I should get a plus 6. Well, here's my plus 12. How do you show a minus 6? Well, you have to think now. What's a plus 6 look like? A plus 6 is a 0, 0, 0, 0, 0, 1, 1, 0. You just invert all the bits. In other words, if you're working with 1's complement notation, you just count zeros as significant. There's your 6 right there, 0, 0. You have to think when you're doing this. This is a negative 6. I add them up. Go ahead and add these all up. And notice you'll get a carry out here from the 8th position. If you get a carry from the 8th position, you have to use this as a correction and add it into this sum. When you do, there's your answer of plus 6. It seems to work. Let's get down here once and take a look at this. Here we have a plus 20, and I have to show a minus 25. Can you see that as a minus 25 right there? I can't. I have to write a plus 25 and then invert every bit on a separate sheet of paper. Don't try to do this in your head. Put down a plus 25 and then invert every bit, and there's your negative 25 in 1's complement. Add them up and see if you get a minus 5. Well, there was no carry to this 8th position, so you don't have to correct down here. I did to show you don't get the right answer. When you don't get a carry on this initial addition, you don't have to, you're adding a 0 down here. You don't add a 1. In other words, you end up with the same number. You have to interpret that now. It's a negative. I know it's a negative number, but a negative what? Well, just look at the zeros. It's a negative 5. It's a 1's complement. It's a negative 5 number, and it works. Keep it in mind, if you don't have a carry, you don't have to compensate. When it's 0, when you add up numbers and you get a 0, you can compensate. Maybe it's easier to see, but you don't have to. You should be able to interpret all 1s as a negative 0. There's a 1 here, compensate. There's not a 1 here as a carry, so you don't have to compensate. Because if you do, you don't get the right answer. This is the right answer here. In the previous examples, this is on page 255. In the previous examples, if you had an initial carry from the 8th position, you always needed to adjust your answer by adding 1. Implementing the logic to do this would require more hardware. Therefore, the 1's complement notation is also not used very often. Well, the sign magnitude isn't used for math at all. It's used for just storing positive and negative numbers. The 1's complement can be used for math, but I showed you, you may or may not have to have the correction here. I want you to try some examples. Here's 4 quick examples I want you to try. Basically, this is what you'll see. I want you to try these guys here. Here's one problem. Try to work it out at the bottom here of the page. Page number 255. Try to work out this problem. Try to do this one. And try to do this one. Try to do these 4. Stop the video and try and see if you get those answers. Notice on the first one here. You have to do this on your own. But this first one, you should get a plus 18, a minus 10. You're going to add them up. You're using 1's complement notation now. I'm not going to trick you and have you try to do anything with math with sign magnitude, because it doesn't work at all. But notice here, when you add a plus 18 and a minus 10, you're going to get this initial carry into the 8th bit. You have to add it in down here for correction. And then you have to interpret that answer. That's a positive 8. It's a plus 8. It works. What about here? Add these up, you should get 0. Well, you can interpret it. I mean, there was no carry here when you added this up. There was no carry from this 8th position. So you don't have to add a 1. You should be able to look at that and interpret that. That's a 1's complement notated number. And it's a negative number. You know, it's a 1 there. It's negative. But invert everything to find out it's a negative 0. It's a 0. If you add 1, maybe you can see it. And you ignore this carry down here when you add this 1 in. Because you're going to get all zeros in a final carry here. You just ignore it. What about a minus 42 and a minus 8? You better get a minus 50 for this to work. Well, I want you to make sure you do that one. There's your minus 42. It's 1's complement now. Write down what a 42 would be, and you invert every bit. You get a minus 42 then. This one you might be able to see what a plus 8 would look like. You invert every bit. 1's complement, that's a minus 8. Add them up. You get this carry out here from the 8th position. You have to add it in, and when you add it in, you interpret this answer. You have to interpret this answer. I'm telling you, that's a 1's complement answer. It's a negative something. That 1 means it's a negative number. You're trying to correlate this with this number here. That 1 means it's a negative number. Then take the 1's complement of that number, and you'll get a 50. I can do that one in my head because it's just the zeros. I have a weight here of 32 and 16 and 2. 32, 16, that's 48, and 2 makes 50. It's a negative 50. I correlated that binary number, converted that binary number to that. Got the right answer. How about down here? A plus 4, a minus 24. There's my plus 4. There's my minus 24. 1's complement. Add them up. I get a 0 here. Don't add that 1. If you added that 1, these answers, this right here is a negative what? This is a negative 19. This is a negative 19. It's surely not the right answer. So what did we do wrong there? You don't need to do this. It's a 0 in the initial carry from the 8th position. There's your answer right there. Interpret it. 1's complement answer. It's a negative. That 1 means it's a negative number. I'm going from here to here. And then that's a way to 16. That's a way to 4. Or just invert the whole number. You'll see you'll get a negative 20. You'll get a 20. It's a negative 20 going from here to there. What we just covered here was, and we did it in less than 20 minutes, we talked about representing sign binary numbers. We said there were 3 notations: the sign magnitude, the 1's complement, But the most important by far that's used in all the microprocessor chips today, and the one that you're going to be most responsible for, is going to be the 2's complement notation. And I wanted to put that in a separate lecture because it's that important. That concludes this lecture.